Okay, hello everyone, I am Sebastiano, and in this video we will see how to set up the remaining part of the case which I showed in the last video. In particular, I show how to use in an advanced manner the block mesh utility in order to make a mesh around a NACA 0012 airfoil. And in this tutorial we will see how to set up the remaining part of the case, and in particular how to set up the dynamicMeshDict, which is located in the constant directory, in order to periodically pitch the airfoil around some points which we will define with an amplitude of 15 degrees. So let's talk about the interpolated solid body motion solver for a few seconds. This is a different solver with respect to others because it doesn't employ an equation which is solved by OpenFOAM as the displacement SBR stress, which we will see in the next video, or the displacement Laplacian, which is very similar. Rather, it uses an interpolation, or let's say a scaling of the motion of the boundary throughout the whole mesh. So basically, three regions are defined, and a scaling factor is defined depending on what regions we are in. So then the motion of the body is multiplied by this scaling factor and applied to the self motion. So in the outer part, the scaling is 0, so the mesh is not moving. In the central part between these two circles, which are defined with two parameters, which are the outer and the inner, which are these ones. In this region, the scaling goes from 0 to 1. So on this edge, the mesh is not moving, and on this edge, the mesh has the same motion of the airfoil. Inside this inner circle, the mesh is rigidly moving as the airfoil. So this is very good because if you have boundary layer cells, or do you want to preserve the mesh near the airfoil, this method, the interpolated solid body, will preserve the mesh around your body. So you might want to choose this because of this feature. And also it allows for very large motion if compared with other motion solvers. So let's have a look at the source code inside the OpenFOAM 8 as RC DynamicMesh motion solvers, displacement, interpolation, solid body, interpolating solid body motion solver, the .c file where all the functions are defined. So this is the constructor of the class, of the interpolating solid body motion solver class. And by the way, here we can see what parameters have to be set in the dynamicMeshDict, which is the file where this function is going to read the parameters. So we have the patches, which are the patches which are moving basically. Then we have the center of gravity, which is a new reference point around which the motion is calculated. So the motion, this is very important because this is somehow misleading, I think, because the motion is not calculated departing from the origin of your reference system, but it is calculated departing of this point. So if you want to calculate the motion departing from the origin, you have to set this to 0, 0, 0. Then you have the DI, which we talked about before, which is the inner distance parameter in the dynamicMeshDict, which is the radius of this circle. So within this radius from the patch, the mesh is rigidly moving. Then you have the outer distance, which is the other radius, the radius of the biggest circle. And then you have other parameters, which are the parameters related to the solid body motion function, which you can find it here. We will use, these are all the possible solid body motion functions. We will use the oscillating rotating motion in order to pitch the airfoil, and you can see which are the parameters which are needed in the blockMeshDict. So here the constructor uses this function read, which you can find it here, and you will have three parameters which are read from a dictionary called solid body motion function coefs, and this is substituted by the type name, which is in the .h file, which is this one. So you'll have a subdictionary which is called oscillating rotating motion coefs, where you will find those three parameters basically. Origin, which is the origin, the point where the oscillation is centered, departing from the center of gravity defined in the interpolating solid body. You have the amplitude, which is a vector, because you could define an oscillation in the 3 direction. Here we will define an oscillation in the y direction, so we have 0, 15, 0, and this value is given in degrees, because here it converts the rotational motion from deg to rad. Then we will have to set the omega, which is the angular frequency of the oscillation. In this video we will set an omega to 6.14 radians per second, which is 60 RPM. It means that we do an oscillation, a complete oscillation every 1 second. So let's have a look at the dynamicMeshDict, which is located in constant, and here it is. We have the library which stores all the dynamic motion solvers FVMesh. Then we have to load the library which contains all the motion solvers basically. Then we have to choose the solver, which in our case is the InterpolatingSolidBody. Sorry for misleading in the slides. Here is InterpolatingSolidBody, because it is basically an interpolation all over the mesh of the motion of the solid body. Then we have to select the solid body motion function, which is, we said, oscillating rotating motion, and then we have to select the parameters of the interpolating solid body class, and then the parameter of the oscillating rotating motion function, which is the solid body motion function class. So we set the patch airfoil, which is the patch which is moving. If you remember in the last video, we defined the name of the patch was airfoil. So we select the patch, one of the boundaries. Let's say if you go into the 0, for example, you have the airfoil. So you have not to define cell zone or phase zone here. the mesh motion solver works with patches, so you have to select the patches. Then you have to select the center of gravity. So I selected 0.5, which is a reference for the mesh motion, which is located at the center of the airfoil, which is which is here, 0.5. Then I set an inner distance of 0.01 meters, which means that I'm putting this circle very close to the airfoil. Then I set the outer distance to 4.0 meters, which means that I'm putting this very far, and I think this is the best solution, because it spreads the mesh motion throughout the whole possible mesh. But you could also lower the radius of the outer distance, but you'll have more deformation, because a smaller area will be subjected to all the deformation, and the coefficient will pass from 1 to 0 very sharply. So this is not a very good idea. Then we have the coefficients of the oscillating rotating motion, which are origin 0.5. So here basically I'm saying that the airfoil is oscillating with respect to the trailing edge, because the chord is 1 here, and I moved 0.5 in the x direction and then another 0.5 in the x direction. So if I want to make the airfoil oscillate with respect to the leading edge, I have to put 0 here and 0 here. If I want to make the airfoil oscillate with respect to the center, I have to put 0 here and then 0.5 here. Then we have the amplitude that, as I said, is in degrees and is a vector. And then I have the omega, which is in radians per seconds, which is 6.28, which is 2 pi. Okay, so the DynamicMeshDict is done. Now I will launch the simulation. I will repeat the passages of the last tutorial. By the way, I forgot to explain the Extrude Mesh, which is useful not in this case, but in cases where let's say you create a background mesh with the block mesh with one cell in the infinite direction. Then you refine the mesh with the SnappyX mesh, for example, because you have to refine the mesh around the body that you want to put in your background mesh. And the refinement in SnappyX mesh works three-dimensional, so you cannot choose to refine only in some direction. So SnappyX mesh will split the cells in the y direction into more cells, and you'll have more than one cell in the y direction, which is a thing that you don't want. So basically you use the Extrude Mesh, you take the surface mesh onto a patch, which is, let's say, a strictly 2D mesh, which is this one, but you have to think about this as a 2D mesh, a face mesh, not a cell mesh. And then you extrude the face mesh in the infinite direction, here would be the y direction, for a certain distance. So you can see that here the mesh was already done with one cell in the y direction. It was already done with one cell in the y direction. So there is no need in reality to use the Extrude MEshDict. But what happens if I put more than one cell in this direction. For example, let's do this very briefly. When I define the blocks, here I have to put 2. This is not parameterized because it wasn't the purpose of this tutorial, but let's do it for clarity. Okay, let's do the block mesh and then paraFOAM again. So let's click apply, and we will see that the mesh has now 2 cells in the y direction. This is not good. So I want to use the extrude mesh to extrude the 2D, the infinite direction face, the face normal to the boundary normal to the infinite direction. I want to extrude this boundary along the infinite direction, which is y here, the y direction, which you can see here, and I want to have only one cell in this direction. So I launch the extrude mesh, and then let's see what happened. Now, okay, now the mesh has only one cell. So this is the purpose of the extrude mesh. But for this tutorial it wasn't necessary, let's say, because we only used the block mesh, in which you can choose perfectly the number of cells in the infinite direction. So now let's run the case so that we will talk about the case while the case is running. So I decompose the case in 4 I decompose the case in 4, and OpenFOAM will create 4 directories which are called processor 1, 2, 3 and 0, because OpenFOAM always starts from 0. In this way the domain is split in 4 parts, and every processor of my computer does the computation on one of these parts. So the time required to compute this case is lowered very much. Let's say that OpenFOAM doesn't have a very good scalability, because it happened to me to try OpenFOAM with very much cores, up to 700, and the scaling efficiency was not very good. But with upon laptops, upon personal computers, let's say that it is good. So now let's run the PimpleFOAM, which is the application that we are using. Since we decompose the case, we cannot just type PimpleFOAM, but we have to use the MPI library in order to launch the application. So we type mprun, we specify the number of processors, PimpleFOAM, and then set the parallel options. Okay, there is an error. Because I didn't load OpenFOAM 8. No. Okay, I have to re-decompose the case again, because I was running with OpenFOAM 6, which I used to open ParaView, which doesn't have this InterpolatingSolidBody motion function. By the way, I just have to copy the 0 directory, because in this way I have an untouched directory, which is this one. If OpenFOAM for some reason puts data here, I can delete it. So now I redecompose the case. Okay, and rerun the pimple form. Okay, it started perfectly. Now let's have a look at the case. So let's firstly have a look at the boundary conditions. We have, first of all, we have the domain was this one. We have the inlet, which is the blue, the outlet, which is the green, and then we have the airfoil. And then we have the back and front, which are the two infinite patches where an empty boundary condition is always used. We have the airfoil, which is a zero gradient, as normal, because with pressure we always put a zero gradient onto the walls. Then we have the inlet, which is zero gradient as well, and then we specify the pressure at the outlet, which is how cases are set up in incompressible flow. If we have compressible flow, we have very big problems on the boundary conditions, but in general we have to specify the variable at the inlet, because if the flow is supersonic, for example, the pressure at the outlet, the information of the pressure which is at the outlet doesn't propagate throughout the domain, because the information travels at the sound speed, and if we are supersonic we go faster than sound speed. Okay, then let's have a look at the U. Okay, here I use, as I explained in my last video, an approach which I like very much, that consists in having a file where I put all my parameters, and then based on these parameters I calculate the more difficult parameter, let's say. So here, for example, that was used for a compressible case. The thermodynamics variables do not make much sense for incompressible cases, but here I set the Mach number, for example, and this expression basically returns me velocity in x and z direction, which I put in the internal field for the initial condition and at the inlet. So I use, in order to do this, we have to write the calc, and then between I don't know how these are called in English, but between this one we have to write basically the expressions. We have to put the dollar symbol in front of each variables, which is called from the initial condition file, and we can use pre-specified functions such as cosine, sine, dec to rad, or the square root. So this is basically a way of setting up the difficult part once for all, and then just set up the easy part, the easy numbers. So on the airfoil we have, this is very important, we have moving wall velocity, which is not a fixed value, because the airfoil in this case is moving, so we cannot fix a velocity value, but we have to use this boundary condition, which basically makes sure that the relative velocity between flow and airfoil is 0 at the airfoil. So this is the condition that must be used if a boundary is moving. We can use this boundary condition also for other application, but maybe we will talk about this in another video tutorial. For example, in racing car application, this is used for the ground. Then we have at the inlet a fixed value, which specifies the velocity basically. At the outlet we have an inlet outlet, which is a Robin boundary condition, which is a zero gradient if the flow is going from inside the domain to outside the domain, and specifies an inlet value if there is recirculation throughout the boundary. So in this case the inlet value is 0. Then this is the back and front, which are always empty. Then we have, let's see, 1.18. I cannot catch this. So then we have the nu T, which is the turbulent viscosity, which is for the outlet and inlet is calculated departing from K and omega, and at the airfoil I specify that I want to use the wall functions. In order to use the wall function, we have to ensure that the Y plus at the first cell centroid is comprised between 30 and 100 or something more, depending on the Reynolds number. For high Reynolds we can arrive to 300, for low Reynolds we are let's say limited to 60, between 30 and 60, but in general yeah, a value between 30 and 100 is correct, unless we have very bad result for the drag coefficient and also the lift coefficient, but this affects very much the drag coefficient. And then if we want to specify a value which is 0, if we would do the calculation and not use the wall function, we would use in OpenFOAM 8 the nu T low re wall function, which basically just compute the Y plus, but lets the user specify the value. Then we have the omega, which is also in this case calculated upon a variable which are defined in the initial condition. We have the Wilcox boundary condition for omega wall, which you can find on the internet. This is the height of the first cell squared and divided by 4, because it would be the half height of the first cell squared, which is calculated based on the grading. If you want, I can give you the expression, not in this video. And then mu val, which is the dynamic viscosity density, in order to calculate the kinematic viscosity. And this is a constant called beta, which is in general 0.075. Then we have another value for the omega at the inlet, which also this one you can find on the internet. There are very much values. In general, if you want to obtain good result, for example for the force coefficient, you have to tune this parameter a little bit, and also the K at the inlet must be tuned a little bit, but this goes out of the purpose of this video. Then we put the omega wall function, which is an intelligent wall function in OpenFOAM, which calculates the value based on the Y plus. Then we have inlet outlet at the inlet and inlet outlet at the outlet. So this is basically the same boundary condition. And then this the same empty for back and front. For the K, we were saying this is inlet outlet for inlet and outlet. This is wrong because I'm using a low re, but we should put instead KQR wall function. KQR wall function. Let me check. KQR wall function. Yes. Let's directly copy this. This is if we put new t low re wall function, this was correct, but in this case this one is good. Now we run the simulation with the bad k boundary condition, but it doesn't matter for the purpose of the video. So now the simulation has finished. You see here, let's talk about the solver a little bit, the numerical solver. Here I'm doing 5 pimple iteration and 2 correctors for the pressure and 0 non-orthogonal corrections. That it means that the pressure is solved once for each corrector loop, and yeah, that's it. One important thing that regards the FV solution, where you can set all these parameters, is that you have to set the solvers for the variables. For the pimple you have to specify the final iteration, because in the final iteration basically is this one, is this iteration here, the last one. Here you have to specify the solvers for the final iteration. Here I put the same, and this p core for which with this point star, which is a wildcard, which means p core and p core final, both are solved with this parameter. This is required if I select the correct phi option. So this correct phi makes sure that the mesh continuity equation is satisfied. That means that when you move a mesh, even if you have, let's imagine that you have 0 velocity throughout the domain and a static mesh, the flux, the velocity flux in each cell is 0. But if you deform the cells still with 0 velocity, you have a net flux into the cells, which is not correct, because the mean cell value must remain constant. So basically this correction adjusts the flux in order to be 0 even if the mesh is deforming. This is called, I think, the ALE method, which basically consists in ensuring the respect of a mesh continuity equation. Then there is the N outer correctors, which are the pimple loop N correctors. You can also set the momentum predictor to yes, which means that OpenFOAM will try a solution for the continuity, for the momentum equation at the start of the time step. And then the N non-orthogonal correctors, which is 0 here because the mesh doesn't have a high level of non-orthogonality. Then another important thing when running with the pimple loop is that you have to with the pimple you can use relaxation factors, which are applied between each pimple iteration, here on the variable and here on the equations, but you have to make sure that on the final pimple iteration you are time consistent. So you have to make sure that you advance with the same amount for each variables and for each equation. So you have to set the p final and the other field final to 1 in order to be time consistent. If you do not put 1 here, you are wrong with the solution of the equation. Then let's have a very fast look at the control. FU scheme is very normal. You can find this on the tutorials, on the OpenFOAM tutorials. I didn't put any strange thing. And you have the control dict, where you have also here I parameterize something. I have the end time, which is parameterized, the write interval, which is parameterized. I write every 0.01 seconds the time, which is, I think, okay for this simulation. I run with an adjustable time step and a fixed Courant-Friedrichs Lewis number of 0.9. With the pimple, you can also go above 1 with this, but in that case, you have to increase the number of pimple iteration, and in order to save some time, put a tolerance that exit the pimple loop if that tolerance is reached. Then you have the functions here, which are for calculating. Oh, this one is not meaningful here. In fact, OpenFOAM should have give a warning. Yeah, here it is. It doesn't find anything of thermophysical properties because this is an incompressible simulation. So this is simply ignored by OpenFOAM. Then we have the residuals, the Y plus calculator, the forces and force coefficients for the airfoil. So let's have a look at the residuals. You can monitor the residuals of the simulation if you go Okay, so let's have a look a second at the case. OpenFOAM created the post-processing folder where the function outputs are stored. So we go into the post-processing residuals 0. Then we use the form. I have it in OF6 form monitor -L, which plots logarithmic in the y-axis residuals, and GNU plot should have plot. Yeah, these are the residuals. So the pressure residuals is very high because I have very bad mesh. So in order to lower this one, you should increase the mesh quality. Or maybe another approach is to, which I tried in another simulation, I leave this here, is to use a higher number of pimple loops, which are 20, and then set, as I said before, residual control on the pimple loop which exits if a tolerance is reached. So in this case you will have a better convergence of the pressure, but not that much because the mesh is the same. So let's see. Yeah, this is with the pimple acceleration, let's call it, and this is without the pimple acceleration for the convergence. So now that we've seen this one, we can go to see the results of this simulation. Okay, now that we have the simulation finished, we can see that into the processor there are the time steps which must be reconstructed, because here there are data related only to the portion of the domain which processor 0 is solving. So this is not the total result, it's a partial result, and we have to reconstruct the result from all the processors. In order to do this, we use the reconstruct par command, which will take a while. This is a very light simulation, so this is very fast, but usually it takes a very long time for bigger simulations. Then we have to use, we have two options here. We have reconstructed all the cases. You see that folders are created outside the processor directories, but I don't like this mess in the case. So instead of using paraFOAM, I'm using foam to VTK, which creates the VTK files to be opened in ParaView. So this is as fast as reconstruct par, and after this we can delete all the folders here, leaving the 0.org folder and also the processors. Okay, now I open ParaView. I load the VTK. Let's put a nice representation. Orientation back. Okay. Okay, now we should see the mesh moving. Okay. The mesh is nicely moving. And now we will play a little bit with the parameters in order to see how they act on the mesh motion. This is the result. Okay, let's change a little bit the parameters. For example, we could want to here we had this dynamicMeshDict. Let's take a solved case where I put, and this one the same, but for example let's take this one where I put the different parameters. So here I put the center of gravity, which is 0, so my reference of the mesh motion is in the same place of the reference of my coordinate systems. So then I have a bigger inner distance, and so the mesh motion will be accounted for by a minor number of cells, and this will provide a more distortive mesh, a mesh with less quality during the motion, because we are making a few points account for all the mesh motion. Then I put the oscillation at the mid chord. So now the airfoil is oscillating at the mid chord, the same amplitude and omega. So let's have a look at the ParaView. It would be nice to open them together. So we open the previous case. And then and then we open the other case. Which is already solved, obviously. Yeah, let's put the black orientation axis and edges 2D. Okay, so here it is. Now we have the two cases, one next to each other. So let's see what happens. Let's compare the mesh motions. You can see that here the mesh is rigid for a very long distance from the airfoil, and then all the motion happens in the last part of the mesh, from here to here. Here the mesh is more nicely deforming, and you can see this looking at the wake of the airfoil. Here we have a very sharp deformation, whereas in this case the deformation is more smooth and very nice with respect to this one. So this is how you can change some parameters in order to have a better mesh quality, obviously, because this must be the objective when you move a mesh. You have to be sure to have at every iteration a high quality mesh in order to have always a good CFD solution. So for this tutorial I think there is no more to say. I will upload the case, I will put a link of the case into the comment of the video. Yeah, please subscribe to the channel and stay tuned for more dynamic mesh videos. Bye bye.